Hello, my friends. This is part 2 in a two-part series on the replication crisis in research that started in the 2010s. By the year 2015, it became very well known. The news about this crisis had spread throughout the academic communities. Measures have been taken to improve it. I am talking about a specific problem of the Bonferroni correction not being applied when people are looking at patterns and data and drawing all kinds of conclusions that aren't true. And what I'm going to do here in part 2 is go over some of the fundamentals about the replication crisis, what things contribute to it, including the new ones, the ones I'm emphasizing that I don't often see mentioned. Just go over this whole issue of the replication crisis in case you're a researcher and you want to be an intelligent reader of research and be aware of some of the things that go wrong with research. So a little background again on the replication crisis started in the early 2010s. Problems were found, of course, much earlier, going back as far as the 60s, but a widespread concern developed in the 2010s. Excuse me. The term p-hacking, which you hear a lot of in research methodology, that was introduced in 2014. So these are all fairly recent things that have come to mind. P-hacking is where you repeat your research over and over again until you get the p-value you want. That's called cheating. But some researchers are cheating and not even realizing how seriously they're cheating. And they're cheating themselves, they're cheating the people who read this, they're cheating everybody. Because they're coming up and saying, oh, I found something when you did not find anything. That's why this is so serious. It's not just some technical, nerdy detail. It's a matter of whether you're saying this vitamin, this mineral, this drug, this therapy works or it doesn't, or do we have any evidence that it works? One of the things that triggered the replication crisis was there were ESP, extrasensory perception, studies that got positive results. And a lot of people said, oh, give me a break, extrasensory perception. And these were pretty wild extrasensory perception results. Like even people that believe in ESP might be like, oh my God, I didn't know ESP could be that strong. And so people took a close look at it and said, well, look at all these methodological problems, all these problems in research. And then they said, well, it's not just the ESP research. We're seeing this in our research as well, in standard psychological ideas. And people investigated and they found these problems. Here are some of the investigations, in case you're curious. I won't read this entire slide from the Wikipedia article on the replication crisis, but in August 2015, the first open empirical study of reproducibility in psychology was published. It was called the Reproducibility Project. So replication or reproducibility, basically the same idea. Psychologist Brian Nosek redid 100 studies in high-ranking journals. Here's the names of the journals. 97 of the original studies had significant effects. So he's looking at 100 studies in high-ranking, prestigious, peer-reviewed academic journals. 97 of those 100 said, yeah, we got really strong effects. When he did a replication study, his team did a replication study, on all 100 studies, only 36% yielded significant results at the 05 level, which is not the strictest level. Wow. That means 2/3 of the studies, roughly, actually didn't find anything. And the mean effect size was half of the original study. So when things were found, they were much weaker than believed. So, yeah, the replication crisis. People are giving an indication they found something when they actually didn't. Another paper in 2012 by C. Glenn Bagley, a medical researcher. C. Glenn Bagley and Lee Ellis found that only 11% of 53 preclinical cancer studies had replications that could confirm conclusions from the original studies. Only 11%. So replication is extremely important, and if the study is conducted properly, the probability of getting a good replication is much higher. When you violate the rules for how to do the research, it's extremely unlikely, as I explained in part 1 of this. So here's some of the things that cause the replication crisis. A lot of these I took from the Wikipedia article, some from other places. The profit motive. When you go into research to make money, there's a conflict of interest. It biases what you're looking at. It biases how you look at the results, etc. So Philip Murawski argues the decline of scientific quality can be connected to its commodification, especially spurred by major corporate profit-driven decisions. So we all know about the pharmaceutical company, other large corporations funding research at universities. There's a bias in the motivation, and that affects the results. Publication bias. Publications often prefer results that give positive results. It's more exciting than something that doesn't give positive results. So they're not publishing the papers that are showing these problems. That's another problem. Another is mathematical errors. People just make mistakes in their math. So you need people to carefully review the statistics and make sure there wasn't a problem. Sometimes the errors are during typesetting, rounding, transcription errors. These are all reasons for the replication crisis. Mathematical errors means sloppy. People are brushing this stuff out. You've got to double, triple, 4 times check everything, make sure it's right. It's not being done, and errors get out there. There's also the publish or perish culture, where professors need to publish to keep their positions and keep their stature in what they do. So they're rushing things out, taking on too much. Another problem is the research article does not provide the data that was analyzed. So nobody can go in with their data and replicate it. They have to collect new data. So there's insufficient information in the research article. People are unable to replicate it without going through a lot of additional work. Another problem is the researchers will blame the statistics. The analogy made in the Wikipedia article is when somebody looks in a telescope and they look up to see what's in the sky, there's 2 things. One is what's in the sky. The other thing is how good is your telescope. There might be things that are there the telescope can't pick up. So you have to be aware of what your tool can do and what it cannot do. And sometimes the researchers will say, it's really there, but, the problem was with the statistics, or it's probably there. It's more likely than the results. And so they're tending to blame the statistics more often than they should. Selective reporting of results. They do multiple analyses. They only do the ones that are accurate. P-hacking, I mentioned in part 1. You keep modifying the research till you get the results you want. Deceptive reporting of results. This is often done with bar charts, where if you just take the top of the bar and you just show that, it looks more exaggerated. We don't have to get into the details. There's lots of information about how to make graphs look more impressive than they are. Sometimes there's outright fraud. I don't think that happens often, but professors under the pressure of publish or perish and publish interesting results may falsify results. Their graduate students who work for them might falsify results because their name is often on the paper as well. I mean, if you're a graduate student, you're hoping to get a position with a company, get a professorship or whatever, work in business. If you have a resume, having found interesting things, it's more exciting. It's more exciting to be the author of a paper that made a discovery than one that did not. Also more likely to get published. So a lot of these biases occur that encourage people to cheat. They can be outright fraud. And then the 2 additional things that I want to mention, the uncorrected p-values in research that identifies patterns in data. So research that goes in with general expectations. There's not even a list of hypotheses. So when you have a list of hypotheses, I'm expecting A, B, C, or D, researchers will always use the Bonferroni correction or other correction for that. But when I'm looking at this data and I see this and I see this and I see this, it's very easy to slip into using the criteria that are used for a hypothesis test. And if you do that, you'll always find something that's statistically significant. I mean, almost always, because if you have 20 things, one of them is likely to have a 0.05 value. So that's the problem. And then, because you're doing knowledge discovery, you're doing this exploratory research, you should be using the rules of exploratory research. Some of the additional rules are you don't need to have, but it's preferable to have theory to support what you find. Does it make sense theoretically? In a lot of the astrology research I've done, they'll say this is going on, this is going on, this is going on, and it's not, maybe it's a new idea or it's a variation idea. It's not like convincingly in the previous theory. And B is even a bigger problem, a lack of theoretical consistency. People are using different settings, what we call different orbs, different tolerances for different variables that are not going by theory. They're just incidental to what's in that data. If you're going to use Sun and Mars and Aries and Leo, which are fire signs, to be just consistent and simple, you should include Sagittarius. All 3 fire signs. If you only include 2 of them, it's just inconsistent. And C, they use weighting, weight certain things more than others, which are likely random fluctuations. So this is all part of overfitting. If you're into data mining, you know all about overfitting. What's happening is people are doing research who are not data miners. They aren't really keenly aware of problems of overfitting and how this is done in a data mining situation. They're actually doing data mining now. You can call it knowledge discovery. They're finding patterns in data, but they're using the rules for the standard rules for a confirmatory test, and they're missing all this stuff. So there's multiple problems, which makes it very clear that if you're making this mistake of looking for patterns in data and treating it as if it's a hypothesis test, the likelihood you found something, that you really found something, that can be found again in a replication study, in most cases is extremely unlikely. You're not finding anything. The problem is not with research methods and science. The problem is with following the rules. The problem is the researchers. They're just not doing it properly. So, conclusion. The main thing I'm emphasizing is this uncorrected p-values, but that's part of a larger issue of what makes a study likely to be replicated. So when new data is gathered, what's going to make it likely that it'll be replicated, and what's going to make it unlikely. And I'm bringing up something that's extremely common in the field I'm in, which is the p-values are not corrected for the fact that the person is looking for patterns in data rather than going in with a strict hypothesis test. And in addition to that, point number 12, they're not doing a bunch of other things that are needed, and it results in what we call overfitting. It's a term we use in data mining, which means you've created a model that fits the data you collected. You fit it to that data, it will not generalize to new data. There are lots of things we do to make it more likely, and those things are being ignored in the field I'm in. And I think it happens at least sometimes in other fields. Okay, so let me just read this conclusion, and we're done with this 2-part series. Uncorrected p-values. In other words, using the p-value that you would use for a hypothesis test, rather than using a Bonferroni correction or other correction. Uncorrected p-values are a common problem in research that identifies patterns in data without first stating a clear, unambiguous, and specific hypothesis prior to looking at the data. Again, the problem occurs when people are looking at patterns and never even state a hypothesis at all. And then they think, oh, let me see what patterns are at 0.01. No, you need to use a much smaller p-value to see something that might be hopeful. In most cases, the confidence level is extremely exaggerated. The confidence level claimed by the research saying, oh, it looks like we found something, very exaggerated, not true at all. Because the number of possible combinations of variables can be enormous. If you're just looking for patterns in data, there's all kinds of patterns you can see. And each additional kind of pattern you see makes it less impressive that you found anything. You know, if I throw dice and I have every possible number except for 2 or 3, it's likely I'm going to be right. That's what's happening. What's happening in this research, it's like somebody throwing dice and saying, oh, I bet I got a 2, 3, 4, 5, 6, 7, 8, 9. Okay, yeah, I bet you did. You know, that's not surprising. You've listed just about every number that can show up. That's really exactly what's happening. And also, let me mention this. Sometimes people start off doing this, looking for patterns in the data, and then they devise a specific expectation, like a hypothesis. They'll say, oh, it looks like this. Here's my hypothesis. Well, if you state the hypothesis in the middle of your research, that doesn't count. As I put it here, devising a specific expectation after exploring the data and removing some variables as potentially meaningful does not absolve the research from this egregious error. You have to have the hypothesis before you collect the data. When you state a clear hypothesis along the way, all you're doing is just articulating what it looks like you found, which is wonderful to do, but you need to collect new data to have any confidence it's correct. So science depends on following proper procedures. These errors that we've identified in research procedures undermine the scientific enterprise. They undermine our ability to make progress and understanding the phenomena being investigated. We're not learning anything. So it's really, really important. So we're not learning anything if you don't follow proper procedures. Well, that's it. I hope that wasn't too tedious, boring to go through, but really very, very important for learning about the world. How does the world work, which is what research tells us, and how important it is to conduct the research properly to learn how things work. And if those become things that people use, especially if they're related to health or anything else like that, we want to get it right so we can really help people. Okay, that's it, my friends. Thank you very much. If you're a subscriber, thank you so much. Subscriptions cost you nothing. You just click on the subscription if you're not a subscriber. And there's also a membership. Some of you are members. It's $10 a month. Meet with me live online twice a month, and I'll answer any questions you have. Yeah, that's it. If you're a member, the meetings are recorded. So if you can't make it live, you can watch the recordings. And you can always send in your questions, even if you're not going to be there live. So, yeah, membership is wonderful. Thank you so much, my friends. God bless. Namaste.